Hello students, this is Dr. Anita Raj, your chemistry mentor, welcoming you for the next part of metallurgy, that is the extraction of the crude metal from the concentrated ore. I have shared the link of my previous video on the first step of metallurgy, that is concentration of ores, in my description box. Please do make use of it for continuity. Okay students, let's move on into the topic now. So this is the topic today, extraction of crude metal from the concentrated ore. Actually, the extraction of this crude metal from the concentrated ore is carried out in two steps, right? The first step is the conversion of concentrated ore into oxides either by calcination or by roasting. Okay, either by calcination. There are two types, one is calcination and another one is roasting. And next step is the reduction of the oxide to metal. Okay, in the first step, we are converting the concentrated ore into oxide either by calcination or by roasting. And the second step is the reduction of the oxide to metal. Okay. So why this is done? Why this conversion of this concentrated ore into oxide is done is actually this reduction of oxide is easier when compared to reduction of either the compound of the metals or the metal itself. Okay, and hence before reduction, the first ore is getting converted into oxide of metal of interest. Understood, students? Why this concentrated ore is getting converted to oxide now? Okay. So now we are moving into the first part of this extraction of crude metal from concentrated ore, that is the roasting. Okay. So what do you mean by roasting? Actually, the process of heating the ore in an excess oxygen supply or air below the melting point of metal is called as roasting. So what do you mean by roasting? It is the process of heating the ore in an excess supply of air, that is oxygen. That too below the melting point of the metal is called as roasting. Okay. Usually sulfide ores can be converted into oxide by roasting methodology. Okay, so this roasting is always carried out in reverberatory furnaces. Okay, so I have shown a picture of this reverberatory furnace. So next we are going to see the changes occurring during roasting. Okay, so what are the changes occurring to ore during roasting? So first one is the moisture. See, the ore will be having the moisture and the moisture will be removed. Okay, and the next step is the sulfide ores will be getting oxidized to metal oxides. Okay, what happens during roasting? So the metal will be getting, that is the ore will be getting converted to metal oxides. Okay, so the sulfide ores will be getting converted or getting oxidized to metal oxide. So I have given three examples now: zinc sulfide, lead sulfide and copper sulfide. Okay, how this is carried out? So this zinc sulfide is getting converted to zinc oxide in the presence of oxygen. So on heating, this gets converted to zinc oxide, ZnO plus sulfur dioxide. Okay, we get sulfur dioxide. So when you balance this, here we want to put 2. Okay, and here also 2. Okay, now this lead sulfide is getting converted. When we heat this gets converted to lead oxide, PbO. Okay, and sulfur dioxide. Here also sulfur dioxide. So in order to balance here, give it 2. Okay, and now the next one is this copper sulfate. So when you heat this in the presence of oxygen, this gets converted to copper oxide, Cu2O. Okay, plus sulfur dioxide, right? So here also we are putting 2. So if you want to easily memorize this, you will not be getting time to balance these equations during the examinations. If not, so it's better to have a just mark it up or memorize or have some idea, right? See, 23, 22, like that, 23, 22, 23, 22. So it's easy to have these numbers so that you can easily finish the equations at the earliest, okay, while writing the examinations. And now next one is the impurities of arsenic, phosphor, sulfur gets removed in the form of volatile oxides. Okay, what do you mean volatile? Vaporizable. Okay, so what happens to arsenic impurities or phosphorus impurities or sulfur impurities? They get converted to oxides, so volatile oxides. So here sulfur, it combines 8 sulfur, it combines with oxygen and it forms sulfur dioxide. Okay, it gets converted to sulfur dioxide. Since it is a volatile oxide, you can put the arrow mark like this. For the gaseous, for gas, we'll put like this upward arrow. For the precipitates, we use the downward arrow. Is it not? Since it is a volatile oxide, we are using this upward arrow. Now, this phosphorus is getting converted to phosphor P4O10. Okay, P4O10. Okay, phosphorus pentoxide, right? So here also, right? And then arsenic, As2, As2O3, As2O3. Understood, students? So here when you balance, we'll be putting here 2, okay, 432, right? 880, like that. So some methodology you should have so that you can memorize this, whatever you should understand, and then you should memorize this equation so that you don't want to spend much time in balancing the equations. Understood, students? So normally this roasting is done in reverberatory furnace, as I have shown the reverberatory furnace earlier, right? Next important method is the calcination process. Okay, so how to convert the what to say concentrated ore into oxide. So the next methodology under this one is calcination. So what happens during calcination? See, it is the process of strongly heating the ore in a limited supply of air or in the absence of air is called as calcination. Either we can use a limited or little quantity of air, or maybe it can take place in the absence of air. Okay, so the process of strongly heating the ore in a limited supply of air or in the absence of air is called as calcination. Okay, now we shall see what are the changes taking place during calcination. Of course, while we are heating, the moisture present in the ore will be getting removed, is it not? So the moisture will be removed. Next, the volatile impurities gets removed. See, when the moisture is getting removed, the ore becomes dry, is it not? When the moisture is removed, automatically the ore becomes dry. Okay, so what happens when the volatile impurities are getting removed? So automatically the ore becomes porous in nature, is it not? It becomes porous. We'll see when the volatile impurities are going out from the ore, automatically a hole will be created. So the ore becomes porous in nature. Okay, pores, we can see the pores or holes. Okay, now next one is if the ore contains carbonates, they get decomposed into oxides and lose carbon dioxide. So if the ore is having suppose the ore is having carbon dioxide, what happens? See this when carbon dioxide will be leaving out while we are heating, so that automatically pores will be formed. Okay. So now we shall see what happens when if the ore is having lead carbonate, or if it has calcium carbonate or zinc carbonate. Okay. So now when this lead carbonate is heated, it gets converted to lead oxide, okay, PbO, and the carbon dioxide will be released. Okay, see from here when one carbon dioxide is released, CO2 is released, it will be having rest PbO. Is it not? So that's what. Okay, so here also the calcium carbonate will be getting converted to calcium oxide. Okay, calcium oxide, and what's the rest of the compound will be? It's carbon dioxide. So carbon dioxide, this is it will be going out. Okay. Now zinc carbonate, when it is heated, it gets converted to zinc oxide plus carbon dioxide. So this is also a gas, automatically it goes out. Okay. So now what happens again? Sometimes the ore may be having hydrated compounds. Okay. Hydrated means it may have water of hydration. Okay. Hydrated ores, what happens when it is heated or when it is calcinated? It expels water of hydration as vapor. Okay, it just what to say, it sends out the water of hydration from the hydrated ore when it is heated. Okay, so now we shall take the example Fe2O3 3H2O. So 3 water of hydration is there. When this is heated, okay, what happens? The water molecules go out. 3 molecules of water goes out. Okay, the water of hydration gets vaporized. Okay, and what we'll have there is Fe2O3. Okay, so only the oxide will be remaining. Okay, if suppose aluminum oxide is there, Al2O3 2H2O. So when this is undergoing calcination, what happens? The water of hydration goes up to H2O, okay, and we'll be having the remaining Al2O3. Understood, students? So this is what happening during calcination. So the carbonates will be getting converted to oxides, so leaving behind carbon dioxide. So carbon dioxide will go out. Again, if suppose hydrated ore is there, so water of hydration will be going out as vapor, water vapor, and we'll be having the oxide. Understood, students? Next important one is, that is the step is the reduction of metal oxides. Okay, this is what coming under extraction of the crude metal from the concentrated ore. The second step under this one is the reduction of metal oxides. Okay, so what happens during this one is the metal oxides can be reduced to crude metal by using a suitable reducing agent like carbon, okay, like carbon or hydrogen or aluminium, and even reactive metals such as sodium can also be used, okay, in order to reduce the crude metal. Okay, so the metal oxides can be reduced to crude metal by using suitable agents. What are the agents? carbon, hydrogen, aluminium, and even reactive metals like sodium can be used. Okay, so now actually what happens is actually the choice of the reducing agent. Okay, so we are using different types of reducing agents. Okay, so the choice of the reducing agent depends upon the nature of the metal. For example, carbon cannot be used. See, this carbon cannot be used as a reducing agent for the reactive metals such as sodium, potassium, aluminum, etc. Okay. Similarly, carbon monoxide, CO, carbon monoxide cannot be used to reduce oxides such as zinc oxide, okay, Al2O3, right? So this carbon monoxide cannot be used to reduce zinc oxide and aluminum oxide, whereas this carbon cannot be used as a reducing agent for the reactive metals such as sodium, potassium, and aluminum. Understood, students? So next we are going to see the different types of reduction of metal oxides. Okay, the first one is the reduction by carbon. Okay, what happens? So see, the oxide ore of the metal is mixed with coal or coke. Okay, see this coal, it's a major composition is carbon. Okay, so this oxide ore of the metal is mixed with coal and then heated strongly in a blast furnace. See, I've given the picture of a blast furnace. So in this furnace, this oxide ore of the metal will be mixed with coal or coke and it will be heated strongly. So what happens? This method actually is applicable to the metals that do not form carbides with carbon at the reduction temperature. Okay. So this metal should not form carbides. So only in that case, the reduction by carbon methodology can be utilized. For those metals which does not form or which do not form the carbides with carbon can be reduced by carbon method. Understood, students? So now here we are having certain oxides like zinc oxide, manganese oxide and chromium oxide. Okay. So now what happens when it is treated with carbon? Okay, when zinc oxide is treated with carbon, it gets converted to zinc and this carbon monoxide is released and of course it's a vapor so it goes out. Okay, and what happens to manganese oxide? This also will be getting converted to Mn. Okay, and the rest will be getting converted to carbon monoxide. Now we want to balance this equation. Okay, see here we are having Mn3, so here we can put 3 and obviously carbon 4 is equal. Here also oxygen 4, so 4. Okay, here 3, here 4. Okay, so 3, 4. Understood, students? Okay, now for chromium is sesqui oxide or chromium trioxide. Okay, plus carbon, it gets converted to chromium plus carbon monoxide. Okay, carbon monoxide. Here also the same thing. It's easy. Here chromium 2, oxygen 3. Then here also 3. So it's easy to balance the equation. So here 2, here 3. Okay. So understood, this is also a vapor. So this is what happening during the reduction of a carbon. Okay. So next method is by reduction by hydrogen. Okay. Actually, this method can be applied to those metals like iron, lead, and copper, which are having less electropositive character than that of hydrogen. Okay. Only to this method type of metals we can apply this methodology, that is reduction by hydrogen. Okay. So what is done during this reduction by hydrogen is the roasted ore is heated in a small tray in a current of dihydrogen. Dihydrogen H2. Okay, dihydrogen gas. Now oxide gets reduced to free metal. See, when the oxide of the metal is heated with hydrogen, dihydrogen gas, we get the free metal. Okay. Now silver oxide Ag2O is taken and it is heated with hydrogen and obviously we get silver, the free metal. Okay, plus water. Okay, so how many 2 here, isn't it? So 2 Ag plus H2O. Okay, now the next one is iron oxide. Iron oxide is also heated with 4 hydrogen, that is dihydrogen. So we will be getting iron Fe. Okay, here also here 3, isn't it? So we can put 3 here plus H2O plus H2O. So in order putting here as 4, okay, here 4 oxygen, so here also 4 oxygen. Understood? So this is what happening during reduction by hydrogen. Obviously, we can make use of water gas also. What is water gas? Mixture of carbon monoxide with hydrogen is called as water gas, and also its water gas is used in metallurgy of some metals. Okay, for example, nickel oxide. See here we have taken nickel oxide. This is reduced by water gas. This is water gas. Okay. This is what mixture of carbon monoxide and hydrogen is water gas. And here also we will be getting the metal, free metal plus carbon dioxide plus water. Okay. So this equation is little important. So 2 So just learn carefully, okay? So just write and see so that you can easily learn the equations, okay? They are simple if you understand the methodology of balancing, right? Okay. Next important method is reduction by metal, okay? See here, this method is used to reduce metal oxides. Normally it is used to reduce the metal oxides which possess very high melting point and are not easily reduced by carbon, okay? So these metal oxides should have very high melting point, okay? It should have very high melting point and also they are not easily reduced by carbon. So in these two categories only we will be making use of this methodology, that is reduction by metal. So those type of metal oxides such as Cr2O3, chromium sesquioxide or chromium oxide is reduced by metal. Okay, so the metallic oxides such as Cr2O3 can be reduced by aluminothermic process. Okay, see actually what is aluminothermic process? The process of reducing the roasted ore with the help of aluminum powder. Okay, with the help of aluminum powder is known as Goldsmith aluminothermic process. Goldsmith aluminothermic process. Okay. So the metal oxide is mixed with aluminum powder here and it is placed in a fire clay crucible. So that's a different what to say, just like a blast furnace or reverberatory furnace or smelting furnace. Here we have a fire clay crucible. So here in this fire clay crucible, the metal oxide is mixed with aluminum powder and it is placed in a fire clay crucible. So now it should be ignited, mean it should be heated, right? It should be heated since it is having high melting point. So in order to initiate the reduction process, an ignition mixture is used. In order to initiate or start the reduction process, an ignition mixture that is usually magnesium and barium peroxide is used. Okay. Now we have taken barium peroxide. Okay, barium peroxide plus magnesium gives barium oxide plus magnesium oxide. Okay, so during this process, large amount of heat energy will be dissipated. So this large amount of heat is evolved, and which this helps in the reduction of this chromium trioxide by aluminum powder. Okay, so this is the process going on. So when this type of reaction takes place, when the ignition mixture is reacting, large amount of heat energy will be dissipated, and that heat energy will be helping the reduction of Cr2O3 by aluminum powder. Okay, Cr2O3 plus aluminum on this on at high temperature gives the free metal chromium plus aluminum Al2O3. Okay, we'll get aluminum. Okay, aluminum oxide. Okay, so now active metals like sodium, potassium can also be used to reduce the metal oxides. Okay, for that we are taking example titanium dioxide. TiO2 is getting reduced in the presence of magnesium, so that it gets converted to titanium or the free metal, and the magnesium oxide is obtained. Okay, so just we are getting the free metal now. Okay, so this is the thing happening during the reduction by metals. Okay. The last one is the smelting. Okay, that's very important. What do you mean by smelting? Actually, smelting during smelting, a flux. What do you mean by flux? Flux is a chemical substance that forms an easily fusible slag with gangue. Okay, gangue itself is a impurity. Okay, and slag obviously it's the final stage or waste product that is produced during metallurgy. Okay, so during smelting, a flux and a reducing agent such as carbon or carbon monoxide or aluminum is added to the concentrated ore, and the mixture is melted by heating at an elevated temperature in a smelting furnace. Okay, see this is the smelting furnace, right? So during smelting, a flux and a reducing agent such as carbon monoxide or aluminum is added to the concentrated ore, and the mixture is melted by heating at an elevated temperature in a smelting furnace. Okay. So what happens during this process? The gangue, it will be combining with a flux. What I told you, what is flux? Flux is a chemical substance that forms a fusible slag with gangue. Okay. So now this is a gangue is a what to say, infusible impurity. Okay, infusible impurity. Okay, it is infusible. When it combines with flux, it forms slag. It forms slag. This is a fusible one. Okay, fusible impurity. This is fusible impurity. Understood. So, when the roasted ore contains acidic impurities such as silica or P2O5, a basic flux such as CaO is used. Understood. So, now I am telling. So, what are the different types of fluxes used? Basic flux and acidic flux. When basic flux is used, if the roasted ore contains acidic impurities like silica or P2O5, we make use of basic flux such as calcium oxide. Now see what happens when a basic flux is used. Suppose if the roasted ore is having silica as a impurity, it combines with the basic flux CaO and it gets converted to calcium silicate, and this is a slag. Okay, this is the last waste product, slag. Okay, so this silica is a acidic impurity. Okay, it is acidic, but this is a basic flux. Okay, now what happens if the roasted ore contains basic impurity like FeO or CaO? We make use of an acidic substance or acidic flux, that is silica is used. Okay, since I have written the same example here, let me convert this to FeO, okay, so that you can understand easily. So this is a basic impurity FeO. When FeO is present in the presence of silica, that is a acidic flux, it will be getting converted to FeSiO3, okay, and this is a slag. Understood, student? This is how we are making use of the acidic flux and the basic flux during smelting process, okay. See here during smelting, this gang or the infusible impurity is getting converted to slag. Okay. So finally the ore gets reduced into free molten metal and the impurities combines with the flux to form the slag. Okay. So both the molten metal and the slag will be getting collected as separate layers at the bottom of the furnace and are taken out from these separate tapping holes. Okay. Well, fine students, you might have understood the different methods of extraction of crude metals from the concentrated ore. We'll meet you with the next step of metallurgy, that is the refining process, in my next video. Until then, it's Dr. Anitara signing off from you. Thanks for watching.